All right, so let's get started. So I confirm now that there are English-speaking people in the course. I will lecture in English if that's okay. That is okay, by the way, because the language of the course is English. I welcome questions in Swedish. I will answer in English, but I will translate if you like. Okay, so the topic of today is actually going into perhaps the most important part of the course, which is to get a good understanding of what a protocol is and how a protocol works on a more abstract level, and then we will go into details as we go along. So today we will talk about something called the OSI reference model when it comes to protocols. Important topics or concepts as services and layering, and a little bit of internetworking. But before we start, some announcements. Project groups will be assigned today, so it should be done by this evening. You will receive an email about this, about who your group members are and so forth, and then you will be called to a kickoff meeting, which will be sometime next week. If you have not received this email, something is wrong, okay? And then we should do something about it. And when we say we, I mean you, because that typically means that we don't know that you exist, okay, if you haven't received the email. So then either it means that there is something wrong with your registration, or for some reason we're unable to see you in ping pong, for instance. So then what you need to do is you need to email Katarina and say, okay, I'm here, I'm following the course, I need a project group. Okay. So let's talk about networks. So what is a network? Typically, we see all of these pictures, the cloud, right? So the cloud is the network, and it's used by applications. Inside the network, there are many, many different pieces. There are nodes, some type of gadgets, physical entities which are inside here. And then there are links interconnecting these nodes. And this could be quite complicated, what's inside here. However, how things are structured to make it useful is one try to abstract the details as much as possible, such that the applications can work without knowing the inner details of the network. So this is a recurring theme in networks, is that one try to make life as easy as possible for the users. And as we will see later on, users, by users we mean both humans who use the network and machines that use the network, but also how the processes, the protocols are using each other. Okay. So at different levels of abstractions, different idealizations of the network will be made. Okay. So there are two types of nodes, those who are called hosts and those who are called routers. And hosts are those machines which are on the edge of the network that are running some type of software which is useful for the users. So for instance, my laptop here is a host, and I don't see it, but the access point to which I'm connected with Wi-Fi, that's a router. That's something which is not running software which is directly useful for a user. And after the access point, there is an Ethernet network, and then there are some switches and all kinds of different things, right? So there are two types of nodes: hosts, which are running software which is useful for a user, and then there are routers, and routers are used to make sure that things are connected, the hosts are connected. Okay, so this is, we will see later on that there are many types of inner nodes here. And some of them are actually called routers, some are called switches, some are called other things, right? But from this point on, from today, or at least for a few more slides, we will divide all the nodes into two main categories: those who are hosts and those who are routers. The component names here are and their functions are not super clear in the sense that there's been a big international congress when one decided, okay, we're going to call these things exactly this, and this is how we define it. So we will see this quite typically, that many things are called by different names, and things which are called by the different names are actually different things. That's unfortunate, but that's how it is, right? So we need to be able to cope with this. So what we need to do is to understand functions, what functions that are needed to be executed in the network in order for it to work, and then realize that there are some things that do this, execute these functions, and these are sometimes called different things, right? But anyways, so if we have some names and some functions and some examples of this might help out to clear up things. So for instance, what is an application? An application or an app or a user, in this course, that means something that uses the network, okay? And examples of applications could be Spotify, Skype, or Amazon website or something like that. A host is something that runs software to support applications, and that could be like a cell phone, laptop, or a server. And other names of host is end system. End system meaning that is typically where communication starts or ends. Or one can think of it as an end system or end node is the same. Source is where data is generated. Sink is where data is consumed. Edge device meaning that these are typically seen as at the edge of the network. We have the inner part of the network, the inner part of the cloud, and then things which are attached on the shall we say, the outside of the cloud. So these who are on the edge. All of these are roughly the same type of devices. And then we have routers, or these could be called switches, hubs, nodes, or intermediate systems. What are those? These are things that relay messages. So they're inside the network, and they receive networks, and they pass them on to their destinations. So that's their task. Their task is to make sure that there is connectivity inside the network and that things end up at the right end system. Okay, so here we can think of a Wi-Fi access points, an ADSL modem, internet switch, whatever. And then we have links or channels, and these are the things which connects nodes. And these could be physical things like cables, fiber optic cables or something like that, or they could be more abstract like a radio channel, which is a piece of radio spectrum. We'll talk more about this later on. Okay, so we have applications, we have hosts, we have routers, and we have links. And this together builds a network and its functions. So communication networks, or the internet, for instance, is immensely complicated, right? Nobody knows how many hosts or how many nodes are connected to the internet. There is simply no way to figure this one out in a reasonable way. There are estimates, of course, but clearly there is nobody who has the blueprint of the internet in front of him or her making decisions on how things are going to be run, right? So this is almost like an organic thing. It's almost alive. It's not alive, by the way, but it behaves almost like that sometimes. So when dealing with, as an engineer, when you deal with problems that are immensely complicated, what do? Of course, we simplify and we modularize, and then we try to solve, we simplify a problem until we can attack it with a reasonable effort. And then we make sure that the subsystems that we design could be glued together such that it can perform a function that we're trying to accomplish. So communication networks are very, very complicated machines, many interacting pieces, hardware and software, routers, switches, cables, radio channels, protocols. It's a big mess, right? The classical approach to this is divide and conquer. Okay, so that's what we're going to do here. And what do I mean by divide and conquer in this context is that the overall problem is so complicated that there is no hope in order to solve it for sure not in an optimal fashion, whatever we mean by optimal, but even suboptimal is very difficult. So what we do, we split the problem into sub-problems. We solve each sub-problem, which is more manageable, and then we glue together all the sub-problem solutions to a complete solution. So this is a standard engineering approach, I would say, right? Now, the step 3 here, of course, means that we need to have very clear interfaces between the sub-problems. Otherwise, the overall, it won't work, right? Okay. So if you have 2 pieces, you should be able to put them together in a way, right? So they need to have a clear interface between them where everything is predefined, so the sub-problems understand each other. So the overall solution to such a divide and conquer is very seldom optimal. Okay, optimal in what do we mean by optimal? Well, for instance, maybe it gives the best possible quality for the resources that we put into the problem, or actually the other way around is more commonly used. That if we want to design a system with a certain performance, we want to do that with the minimum number of resources allocated to this. And resources could be hardware, software, energy, materials, or whatever, right? Okay. So the overall solution is very seldom optimal if we do this. However, it has some clear advantages: modularity and flexibility. And modularity means that if we are redesigning a sub-problem, the solution to a sub-problem, that does not affect the whole overall system. So we can exchange pieces of the overall solution without jeopardizing the overall function. So that's one thing. And then also flexibility is that one can, take things and rearrange them in reasonably easy. Okay, so we're gonna take this approach to heart and see how we can do that in order to design a network to perform some functions for us. Okay, so this is probably the most important slide of the first part of the course. So I want you to take this to heart. If you can understand this, much is gained. Okay, and then of course we will go into more and more details to explain what is meant by this slide, right? But the overall picture is here. Okay, so in communication networks, the overall problem is divided into sub-problems called layers. Okay, and layers are stacked on top of each other. So we have layer 1 at the bottom, layer 2, and so forth, up to layer n. Okay, and the number of layers depends. It could be different for different types of networks. Okay, now, so the numbering is important. So layer 1 is at the bottom and layer n at the top, and they are residing on top of each other. So sometimes this is also called a stack, a protocol stack. Okay, so inside the purpose of a layer is twofold. It should provide a service, and it should provide it to the layer above it, and it does that by using the services of the layer below. So layer 2 here, for instance, is providing a service to layer 3. So layer 3 can use layer 2 for something, right? And this service is provided using services from layer 1. Okay, so layer 2 uses layer 1 to do something for layer 3. Layer 3 is using layer 2 to do something for layer 4, and so forth. Of course, the poor layer 1 here has to do all the work itself, right? Okay. Each layer operates according to a protocol, okay? And a protocol is a set of rules that defines how 2 or more communicating entities in this layer interact, okay? And we will see this will be made a little bit clearer later on, but let me try here. So layer 2, for instance, layer 2 resides physically in some node in the network. At some other node in the network, there is also a layer 2. So this layer 2 would like to talk to that layer 2. So we have 2 layer 2s, one at node A and one at node B. They want to talk to each other, and they talk to each other according to the rules which are decided by a protocol which resides in this layer. Okay. So a A protocol is a set of rules for how two or more entities, and entities are software pieces which are running in a layer. Okay, we can think of that as software or a process which is executing this protocol. So here we have more than one program. These programs are run at different computers, and they want to communicate with each other, and they communicate using the rules which is defined by that protocol. Okay. A set of layers with protocols is called a protocol stack. Okay. So when you get home this evening, you can pull up this slide again and see, okay, did I get this? Right? And if you did, you're in good shape. Okay. So now over to more details. And let's do an example, for instance, to illustrate what we can use the network for, and we use this almost daily, web browsing. So what is going on here, really? First, what is the web? Well, it's a bunch of servers that has documents. And these documents are HTML documents, so they're encoded using a certain syntax. And there could be other resources like pictures, videos, and audio, and so forth. And they're located at servers, and these servers are connected to the internet. Okay. These servers are hosting data, so they're an application. So these are hosts. These servers are hosts. It doesn't really matter for this example. Okay, a browser is a piece of software which is running on your device. So it could be Chrome, Firefox, Internet Explorer, Safari, Opera, whatever you use, right? And it's used to locate and display documents. Okay, so it's a user interface in a sense. What is a resource? That could be some of these HTML documents or something. It's specified using a certain syntax according to the uniform resource locator. It's called a URL, all right, or a link, whatever. And it consists of a number of paths, a number of parts which are important for the operation of the network. First of all, this first part here specifies the protocol, in this case HTTP. The second part here defines a host on the internet. So www.chalmers.se. It's a host, it's a server somewhere that has all the documents which belongs to the Chalmers web. And then there is a path on that server that specifies a specific document, in this case svcdor default.aspx. Okay. So when a user clicks on a link which contains this URL or types it into the address field and hit return, what does the browser do? The browser then finds the IP address of this host, connects to the host, and then requests the file and then display the results. These are the steps. Right? So let's see in more detail how this is done. Right? So number one, find the IP address. And the thing is that computers that are hosts that are connected to the internet could be found by addressed by their IP address. So internet protocol address. So when the user clicks on the link here, www.chalmers.se, that link or that name, www.chalmers.se, is the internet name of the server. And that's very useful for us as humans, right? Because we can understand, okay, this is a web server, it's Chalmers and it's located in Sweden. There's Chalmers is located in Sweden somehow. Okay, so it's useful for us, but it's no use for the internet in order to find it, or it's not useful for the IP layer to find this host. Okay, so we need to translate, to connect to the server, we need to find its internet address, its IP address. And the browser uses then a specific protocol to figure this one out, and it's called the Domain Name System, DNS protocol, to look this up. So how it works is that there is a server, a DNS server here, which has a table which translates between internet names and IP addresses. So if the web browser does not know the IP address, it needs to ask the DNS server, could you please tell me the IP address of this server? So the web browser then sends a query to the DNS server. So it uses DNS, it's a query, and it asks, so could you tell me something about this host? The DNS server looks up in its database and if it finds it, it sends it back. And it sends back a reply message, DNS answer, and says 129.16.71.21. Okay, so this is the IP address of this one. Okay, so it happens to be that somewhere on the internet there is a server who has this internet name and this IP address, and this record is stored here also. So we can think of this as a directory assistance, right? So if we don't know where to go, we ask the directory here. Secondly, Secondly, what happens then? We need to connect to the server. And so what the browser does then, it opens a connection to the server using another protocol called Transmission Control Protocol, TCP. And applications on a server are addressed using port numbers. Okay, so there on the server there could be many applications running, web server being one, could be other types of servers there. These applications are addressed using port numbers. And for some reason, people have agreed upon that web browsers listens to port 80. That's well known. Everybody knows this. Okay, so this is not a mystery to our web browser. It knows this. So the web browser can then connect to port 80 on the server, and it does that with a TCP connection request. So what the web browser does is that it asks it TCP protocol at the local computer, could you please connect me to this IP address? Could you please connect me to this IP address with port 80? Okay, and then one also has to say from where you are. So TCP, when it sends a connection request to the web server, it has this comes from the machine with the IP address 127.0.01. I just made this up, right? So, okay. And then one also has to say which application on this server, on this computer, would like to use this TCP request. And that is then defined by a port number. And this port, the web browser here does not have a fixed port number, so it just invents one randomly from a pool of port numbers. So for this particular case, it just randomly selected port 1127. Okay, so when we sent this request, or the web browser sent this request to the server replies typically yes, it's okay. Right? But it could also refuse it. But then if it says, okay, TCP connection is okay, then we can start to communicate. Okay. So this is something called a connection-oriented protocol, because before we even send any user data, the protocol establishes a connection between the endpoints. Okay. So if you remember back from the first lecture, this is similar to what you did when you did a phone call. You put up the hook of your telephone, you dial the number, and so forth, and then a connection is established in the network before we can start to communicate. And this is quite different from a connection-less protocol where we just send data without even connecting to the server. So we just push in data into the network and hope that it arrives at the receiver. Okay? Okay, so now a connection between the web browser and the web server is established. And now it's time to fetch the file. Okay, by the way, this TCP interaction here is greatly simplified. Okay, so there are some data going back and forth here, but this is the gist of it. One makes a request and then gets a okay or a denial on this. Okay, request the file. How's this done? Then we use the web browser uses another protocol called HTTP in order to request files. And it's quite simple protocol, as we will see. So applications, again, are addressed using port numbers, and we know that the web browser is using port 80, and the web browser has used this temporal or ephemeral, as it's known also, port number. So ephemeral here means temporary. Okay, so it's a fancy English word. I don't know if you knew this. I didn't know it before I read about that. Anyways, so what happens is the web browser is then sending a request using its TCP connection to the browser, and it says, get this page, please, and I'm using this protocol because there are different versions of HTTP, right? Which means that there are slightly different rules. Okay, so this is also good to know. Protocols are not static in the sense that they are defined once and never changed. They evolve. Okay, they evolve as technology evolves, and they also evolve as needs evolve. Okay, so the current HTTP protocol, or the most common one, is 1.1, and there was 1.0 at some point, I guess. Okay, so it says, please get me this page, and then it says, okay, I'd like to get this page from this server, this host, www.chalmers.se at port 80. Okay, and then if the web server actually finds this file, it says, okay, 200 means here that things are good. Okay, and here's the file. Okay, and that's it. So what happens then is that, okay, there is this interaction is a little bit simplified. And what happens then is that the web browser takes this file, parses it, and displays it to the users. Right? So this is a typical interaction over the internet using different protocols, okay, which we don't know how they work. Right? But the cool thing about the internet is that it's live. We can actually do this without any particular software, so we can try things. So let's try to do this, but let's try to mimic the web browser. So I'm the web browser now. So I'm going to type in some commands in a terminal to see if we can actually execute these things, and then you can try yourself if you like. Okay, so if we remember what we want to do, we want to do 3 steps. We want to find the IP address of the Chalmers web server. We want to connect to it, and we would like to request a page. Okay. Oops, I don't want to do that. I want to. Is that big enough? Okay. All right, so let's see if I can do this. It's always exciting because there are many ways you can do this wrong also. But the first thing we need to do is to figure out the IP address. And then on the Mac, there is a program called dig. There are other NSLOOKUP on Windows. There are many different programs that can do this for us. And essentially what they do is they connect to a DNS server and then ask the DNS server for something. So in this case, I would like to have www.chalmers.sc. Okay. So here's the response. It's quite verbose. Dig gives us more information than we probably want, but let's see what's going on here. So it says here is dig, and you ask for this. So the question is www.chalmers.sc. We would like to know this, and here's the answer, and here's the IP address of it. Okay. Then it told us many other things, right? But here's the IP address. So now we know the IP address. So the next thing we want to do is to use TCP to connect to this server. Okay. There is a program called Telnet that could do this for us. So Telnet, and that's a very, very old program. So it's available on most computers, I would say. Okay, so let's see what we should do now. Let's see if I can remember the syntax. We should, let's see if this works. We want to go to 129.16.71.10, and we want to connect to port 80. Okay? Yay, it worked. Okay, so now we're connected. So the next thing to do is to get the file. Okay, so I'm now using HTTP syntax. So get, and then what was the name of the file again? It was called dash sv dash sidor dash default .aspx And then I want to use the protocol HTTP version 1.1. Okay. Okay, thank you. What's wrong?
HTTP, not HHTTP.
Thank you. TTP 1.1. Like that? Okay, let's commit. And then I also want to say which web server I'd like to talk to, because at an IP address there could be several web servers running. Okay, and the syntax here is host www.chalmers.se, and then I need to specify the port here also. Okay, so now I sent these two messages, and to execute them I send a blank line also. So let's see if it works. Yes, it did. Now it's quite big, the first page at Chalmers. So here is all the blah blah blah. But if we just look at the header here, okay. So remember that we just did this, and then a blank line, and here's the response from the web server. It says it's running HTTP 1.1 200 OK, and here comes the file with some metadata first. It tells us a little bit of what it is. That's HTML, and it has an expiration date. This is the name of the server. This I have no idea what it means. Needed this, well, sort of, right. And the date, and then the content length. So this first web page is 63,950 bytes long. And then here it is, right? Obviously, this is not for human consumption, right? But Firefox or whatever could interpret this and then display the nice first page of Chalmers. So this is, I mean, it's cool. You can work with these things. And I encourage you to do that, because that's a great learning experience. Because then you would see also that things I'm telling you in class are actually more complicated in reality. But of course, I cannot tell you exactly how things work, because then it makes no sense. Right? It's like we cannot explain the concept of a forest by looking at the individual trees in great detail. So what I'm going to do, I'm not going to lie to you, but I might not say the entire truth. Okay. I think that's typical for any course, actually. Okay. If you remember your courses in high school, for instance, I didn't tell you all the truth either, right? Parts of it, maybe. Okay, so now we know firsthand a little bit of protocol, but how this is all work together. And how comes the layering into the case here. So let's see. We did this. So we used HTTP, DNS, and TCP, okay? And here's also typical when it comes to computer networks. There are acronyms everywhere, right? So at some point you forget what the acronyms means. So two network experts that talk to each other could be, I mean, it's riddled with acronyms. So that's a difficulty, of course, for an outsider to understand. But anyways, we used HTTP, which is Hypertext Transfer Protocol, DNS, and TCP. And how does these relate to layers? Well, let's talk a little bit about layers and services. So remember that a protocol is a set of rules that defines how two communicating entities are exchanging information with each other. So they are communicating and they are placed in the same layer. So this is important. A layer, when in a protocol stack, we have a layer here. The protocol entities here are, of course, communicating up and down in its own protocol stack. But when it's communicating with some other node on the internet or on the network, it only talks to that same layer. Okay. So in layer N, for instance, here at node A, there is a protocol entity A. So this is some a software process, and it talks with the corresponding entity, protocol A entity at layer N at some other node B. Okay, it doesn't talk to the upper or lower layers here. It talks with the same layer. Okay, so that's one thing which is important. And the language it speaks is defined by the protocol. So the messages that goes back and forth between these two computer programs or computer processes are defined by the protocol. And that could be HTTP, for instance. or DNS or something like that. In the same layer, there might very well be another protocol, protocol B, which is talking to protocol B, maybe at the same node or at some other node. We don't know, right? But the thing is that's important is that protocols are speaking using a language which is defined by the protocol, and it's speaking with its peers, its same protocol entities at other nodes. And these peers are located in the same layer, okay? So messages are sent and received, and then actions is made according to these rules, right? So there could be events. How does protocol, this entity behave? Well, it depends on the messages it receives and also on timing information. There could be, you know, something coming from the upper layers telling it to do something. It could be something else that happens also, that you requested a file and that file does not arrive within a reasonable amount of time, then you abort. Okay, so there are many things that could happen that tells a protocol to do something. But they are events of some nature, sending or receiving messages or expiration of timers or whatever. Okay, is that clear? Please interrupt if I'm unclear, right? Okay, so the purpose of the protocol, again, is to provide a service to the layer which is above using the services which are below it. So the only reason that these protocols live is because they want to serve the users or the protocols which are on top of it. That's the only reason they are there. Okay. So on top of the protocol stack, it's called the application layer. So that's the top. And both HTTP and DNS are application layer protocols. Okay, so what does that mean? Well, it means that HTTP and DNS provide some services, communication services, to application programs, so web browsers, email clients, and so forth. So here we have the user programs, say a web browser, and it uses the services of the application layer, for instance, HTTP or DNS, in order to do its task. Okay? So Firefox, the web browser, for instance, is not an HTTP protocol entity. It uses the HTTP protocol entity in order to request files. Okay? So there is a separation between the user software and the application layer protocols. Okay? Sometimes this is confused. Okay, so anyways, yes. So the web browser software is using HTTP in order to transmit messages back and forth to the corresponding application layer at the web server, and the web server software is connected to the HTTP protocol here. So a request goes down like this, and then up like this, and then things are moving back and forth, back and forth, back and forth, right? So, and this abstraction level makes it easier for life easier for those who program these web browsers, right? They don't need to understand how the data is actually transmitted, if it's going over a fiber optical channel or whatever. It just needs to be able to talk HTTP. Okay. Then, of course, how are things done in practice? Well, HTTP does not magically transfer information according to these dotted lines here. This is only the logical connection. The physical connection is actually going down to the layer below it, right? So the application, the protocol HTTP is using TCP in order to transmit its messages. Okay, so the request, this GET message here, is actually going over TCP using TCP messages, using the protocol TCP. So TCP is in what's known as the transport layer, which is just below the application layer. So HTTP is using TCP in order to do its work. And then this continues. Okay. So to summarize, web browser has a task to do, and it's using the services of the application layer to do its job. The application layer protocols, to do their job, they are using transport layer protocols in order to do its job. And you might guess what happens with the transport layer. It's using a layer below it to do its job. Okay. And so these dotted lines here are logical flow of information, not physical flow of information. But it's very useful abstraction. Okay, so a quick quiz here, and I mean, you don't get credit for this, but just to figure out where you stand. So if I'm asking you here, what is true? A layer can contain many protocols. A protocol can span many layers. There is exactly one protocol in each layer. So I'll let you think for this for 10 seconds, and then we'll have a vote. Okay, it's only 6 seconds. So who's for number 1? Who's for number 2? And who's for number 3? Excellent. So a layer can contain many protocols, but a protocol does not go in other layers. It stays in its layer, and there are many protocols per layer. There could be many protocols per layer. Great. So here, what is true by an application program, for instance, a web server? Is it a protocol in the application layer? Is it using the services of the application layer? Or is it providing a service to the application layer? Who's for number 1? Who's for number 2? Yes. Who's for number 3? Excellent. So you got that too, right? Because this is a common misunderstanding, that one thinks that user software is running in the application layer. It's not. At least not in this course, it's not. Okay. So what is the main purpose of a layer? To provide a service for the layer below it, to interact with the corresponding layer at some other computer, to provide services for the layer above it. Who's for number 1? Who's for number 2? Who's for number 3? Yeah, great. So this is true, but it's not the main purpose. Here's the main purpose. Great. I think we deserve a break. Kan du trycka på röda knappen där? Ja, på andra sidan batteriet där. På... Där, stäng.